Okay, so welcome everyone for this edition of the BRAG. And today it's my great pleasure to introduce my colleague Eduardo Esteves from IMPA. He will speak on the generations of line bundles on curves. Go ahead, Eduardo.
Okay, thank you, Carolina. Thank you for the invitation. It's a pleasure to speak to all of you here. And I'm going to talk about joint work with Omid Amini from the Ecole Polytechnique. The title is Degenerations of line bundles on curves. So I will state what we prove. And what we prove is exactly this. We describe explicitly collections of degenerations of line bundles over families of smooth curves. So maybe the drawing explains this a bit. I have a family of curves over a punctured disk, B star, and of smooth curves. I can extend this family by stable reduction, modulo base change, to the center of the disk by adding a stable curve. And if I have a line bundle or a family of line bundles over X star over B star, that means a line bundle for every curve of the family. The question is, what does it extend to over the whole of the whole family? Okay, so over this potentially singular curve over the center. Okay, so this being algebraic geometry, I will translate everything in algebraic geometric terms. So instead of looking at the disk, I can look infinitesimally and then consider this the power series ring in one variable. I'm over an algebraically closed field, K, with any characteristic, not necessarily C then. So B has just 2 points, and the general point I'm denoting by eta. I have a family of curves, which means a flattened projective map. I'm already considering it extended over the whole disk or the whole power series. So as I'm looking infinitesimally, there is just a general fiber, which I'm assuming to be smooth. And the special fiber, which I will assume that it's nodal, a nodal curve. So the singularities are just ordinary singularities. The special fiber can be irreducible, but it can also be reducible. And I'm considering an invertible sheaf on, in principle, it should be on the geometric general fiber. But if I'm over a field of characteristic 0, then that would be an invertible sheaf on this extension of the field of Laurent series. So just take some nth root of t. So it's the invertible sheaf, and I want to know whether it extends in some way to the whole thing. So since we're dealing with abstract data, sheaves, I mean, it's really an open question, I mean, to what it extends to. But following Meyer and Mumford, their suggestion in the 60s, I will consider torsion-free rank 1 sheaves. So I will consider the relative space of torsion-free rank 1 sheaves. So I will in a minute explain what these sheaves are. They are special coherent sheaves that are commonly used to compactify invertible sheaves. Okay? So there is this space, J bar X over B, whose fibers are parameterized torsion-free rank 1 sheaves over the fibers of the family. And since I have an invertible sheaf, which is torsion-free rank 1 on the general fiber, I can consider the point corresponding to it, and I can consider the closure. So in algebraic geometry, we take the limits by taking the closure and restricting to the special fiber. So this Z here, it parameterizes the limit of the invertible sheaves. Okay? So this is our statement, joined with Omid. That Z is a connected closed substack of J bar of X of pure dimension 0. More than that, it's the quotient by a torus of the toric arrangement associated to a certain polytope decomposition of Euclidean space. So what I'm going to do in this talk is to unravel these statements here. Let me just say that it's a very precise statement, so that's why I'm emphasizing certain. We actually describe the polytope decomposition and the corresponding toric arrangement. And more than that, we classify all of the z's that arise in this way. So I can give you a certain quotient of j bar of x, and I can tell you that, okay, that quotient arises as the limit along a smoothing of the nodal curve x and some invertible sheaf on some extension of the field of the generic fiber. Okay, so that's the statement, and let's pause a minute to look at this statement and to understand what's going on. So first of all, this j bar of x, even over the nodal curve x, so maybe I can use this here. So here, this j bar of x is a stack. So usually when you hear the word stack, you hear two names, Deligne and Mumford. And Deligne and Mumford stacks have been studied, and they're quite nice. But the fact is that this is not a Deligne-Mumford stack. It's just an algebraic stack, or sometimes called an Artin stack. And that's because the objects it parameterizes, these torsion-free rank point sheaves, they can have large automorphism groups. Usually you get a Deligne-Mumford stack when the automorphism group is finite. That's not the case here. Okay? So it's not a nice, maybe geometric object, but it has some geometric structure. It's an Artin stack. So all of you, maybe who have studied the problem, know that there are difficulties that arise when you consider curves with several irreducible components. So if x is irreducible, has just one component, then everything is fine. Everything is a scheme. J bar of x is what is known as the compactified Jacobian, is a projective scheme, right? And this is a point. Now, when the curve has more than one component, some problems arise, some difficulties arise. And I must say that this stack, j bar of x, solves none of those difficulties. In fact, j bar of x, this scheme here, this stack, sorry, is non-separated and has infinitely many components. And it's not a scheme, it's a stack. The same holds for z, actually. One could hope that z maybe were a simpler thing, but it's not. It's also non-separated. It has infinitely many components, and it's not a scheme. And in fact, I mean, it couldn't be a scheme. How many schemes do you know which are connected and have pure dimension 0? Just a point, right? So, so that's one caveat about this theorem there. So what I want to do, I mean, and that's the outline of the talk, I will motivate the problem. Then I will describe what this polytope decomposition, what z is. And in the third part, I will explain what we can do with this z. So what kind of constructions and maybe applications we can think of. Okay? Any questions so far? All right, so let's move on.
Eduardo, yes. Excuse me. Eduardo, you said that the curve may have several components, but the curve can also be non-reduced?
No, I'm considering just reduced curves. So non-reduced curves, I mean, yeah, no, I'm not considering those. I never consider those, so that's the answer. Yeah, might possibly be. But
thank you.
Yeah. Any more questions? Okay, so let me talk a bit about the motivation. Okay, so it's a general statement here. that the study of degenerations of line bundles is kind of old already and has found substantial applications. So the Brill-Nutter theorem was proved using degenerations. Also, the birational geometry of the moduli space of stable curves is studied using degenerations as well. So it has applications. And it's also known, as I write there, as this pursuit of natural compactification for the Jacobian. So let me just explain this. So if you have a projective reduced connected curve, you can consider its Jacobian, which parameterizes invertible sheaves on X of a certain degree, or you can fix the degree if you want. That's the Jacobian. It's a quasi-projective variety. Yeah? And then the question is to construct a compactification for that Jacobian. So we'll put some names here. So as I said, it's a node problem. Ikusa was the first to study it. He studied degenerations by studying Lefschetz pencils. The singular curves that appeared were irreducible and nodal. Meyer and Mumford, as I mentioned before, suggested that putting at the boundary points that parameterize torsion-free rank-bound sheaves. That suggestion was carried out by de Souza, an Indian mathematician in the 70s, using geometric invariant theory. A few years later, Altman and Kleiman gave two different new constructions, more direct constructions of the compactification for families of curves as well, but always irreducible curves. Old and Seshadri were the first to, and I just learned that Seshadri died very recently, so it's a pity. So, yeah, so just mentioning here. But it's a very fundamental work in the 70s. They were the first to study the compactification for reducible curves. And I must mention Caporazzo's work. She constructed a relative compactification of the Jacobian over the moduli space of stable curves in the early 90s. Okay. So it's a question that has been pursued by a lot of people, and an important question. I said that I was going to explain what a torsion-free rank-bound sheaf is. Well, it's better to explain by example, I guess, maybe, but that's it. I mean, if you have a finite subscheme, the ideal sheaf, the sheaf of ideals, is torsion-free rank-bound. It's actually invertible if F is a divisor, an effective divisor. So you can see why Meyer and Mumford made this suggestion, because you can have a subscheme, which is a divisor, degenerate to something which is not locally principal, not a divisor. Right? Then you can look at the ideal sheaves and look at the degeneration of the sheaves. And in general, a torsion-free rank-bound sheaf is just a modification of the ideal sheaf, just by transferring it's an invertible sheaf. These are all of them. Now, sheaves are abstract things. We actually study invertible sheaves because they are related to concrete things. In fact, the Jacobian can be viewed as parameterizing equivalence classes of divisors on your curve. Right? So divisors are subschemes, and you group them in certain classes, which are these rational equivalence classes. These classes are projective spaces. And the real question is what happens with those projective spaces of divisors when you degenerate a curve? So what do they go to? What do these divisors go to? Talking about the limit, the degeneration of a sheaf is an abstract thing, right? But talking about degenerations of divisors, of subschemes, that's something very concrete. They admit just one possible degeneration. So the question is what to make of all of these degenerations of divisors. To be more concrete, I will present an example, which is likely the simplest example there is of this issue, because I'm dealing with conics here. So what I have is a pencil of conics, And I have a singular member, which is a union of two lines, L and M. Right? And that's my family of curves. And I'm going to consider the linear system of lines on this family. So a line is a divisor on the whole plane, but I can restrict to the family of curves. So for instance, this line N here, it intersects the union of the two lines in those points P and Q, and that's the divisor on the union of the two lines, P plus Q. Now I can consider not just a single line, but a linear system, or a pencil of lines. So I'm considering here the pencil generated by L and N, right? Which is just the set of lines that rotate around the point Q, the base point of the pencil. So I can look at the intersection of these lines with a general member of the pencil of conics and look at the degeneration of that. So here I do this for the line N of my linear system. So I look at the intersection of this N with Lm plus Tc, right? And let T goes to 0. Okay, here it's the same thing as making T equals to 0. And then I get the points of intersection P and Q. If I pick another member of this pencil of lines, which is L, and I do the same thing, now I cannot simply make T equals to 0 because L is part of L times N. But I can look at the intersection for T non-zero, right? And take the limit. Well, you see that I can just subtract a multiple of L from the left here. Oh, I can use this now. I can subtract this here, and that intersection is actually constant. It's the intersection of L with C, which is R and S in the drawing above. Okay, so it's actually a constant family of as T goes to 0, and the limit is R plus S. Now, the thing is that R plus S is not the limit of P plus Q and N goes to L. So I had something which was a connected thing. It was a P1, the linear system before, generated by L and N. And in the limit, I get something which is not connected at all, because the limit of P plus Q is just Q plus the node. It has nothing to do with R and S. And in fact, it's not easy to put these things in the same rational equivalence class because it's not possible. You see, P and Q are distributed. P belongs to M and Q to L. So P plus Q is a divisor of multi-degree 1, 1, whereas R plus S has degree 2, 0. So the numerical invariant doesn't allow that they be rational equivalent. So how to deal with this? So the solution that has been generally given to this problem is to pass to the sheets and simply forget some of these multi-degrees, to concentrate on some specific multi-degrees. And that's given in terms of a polarization. So I'm going to talk about polarization now. Before that, any question about the example? We're going to come back to the example. But let's look then at, how the compactifications of the Jacobians have been constructed for reducible curves so far. So they made use of a polarization. So what's a polarization? A polarization is the following. You have your nodal curve X. You call V the set of irreducible components. A polarization is just simply a function on V with values on Q, the rational numbers, such that the degree, which is the sum of its values, is an integer. So an example is the canonical polarization. So you can pick the canonical bundle on the curve X, which is a bundle, line bundle, if X is Gorenstein, and look at its degrees on the components and use them to construct your polarization. If you do that, you're going to get a polarization of total degree 2G minus 2, where G is the arithmetic genus. Okay? If you want, you can scale this polarization by any integer, and then you get a polarization which has rational values and has total degree D. So that's one way of getting a sort of canonical polarization for every degree. And using the polarization, we define semi-stability. So basically, if you attended talks on moduli problems, this is a word that appears everywhere, stability. And it's how moduli spaces are constructed in general. So I define a torsion-free rank point sheaf I to be Q semi-stable if its degree is the same as the degree of the polarization as a whole, but the partial degrees are not equal to those defined the polarization, but they are close. So we have this inequality here that Caporazzo calls the basic inequality. So this is an inequality that should hold for every proper subcurve. So let me explain the terms here. So Y is a subcurve, which is just a union of some irreducible components of X. This delta of Y to the right is the number of points of intersection with the complement. If it's a scheme, you can pick the length of the intersection if you want, but for nodal curves, it's just the number of points. This Q of I is the degree of Q on Y, that is the sum of the Q of V's with V in I. And this I of Y is this torsion-free quotient of I. So it's the restriction to Y modulo torsion. If I is given as an ideal sheaf, that's how you obtain I of Y. You just restrict your subscheme to Y and do it. So, and the degree is what makes Riemann-Roch work. So it's just this difference of Euler characteristics. Okay, so these inequalities should be satisfied. So that means that the numerical invariants of your sheaf I shouldn't be far from those given by Q. That's the thing. And actually, if you have an invertible sheaf, and if that invertible sheaf has degree equal to that of the polarization on every component, then I satisfies the inequalities. In fact, the absolute value is 0, and it satisfies the strict inequalities, and that's the stability notion. So a sheaf is stable if the inequalities are strict. So that's the notion of semi-stability. You notice that it restricts the kind of degrees that your sheaf has on the components. They must lie in this range given by this delta of Y and the Q. And using this notion, Lucia has constructed what I said, a projective coarse moduli space of semi-stable sheaves with respect to the canonical polarization in any degree D over the moduli space of stable curves using geometric invariant theory. So that's a very interesting compactification. It's the first one that was constructed. It uses this notion of semi-stability. But what I claim is that if I want to study divisors, the notion of semi-stability is not so useful. So even though the union of two lines in our example is not a stable curve, let's look at that as an example. You see, I mean, I can look at the union of two lines and I can consider the canonical polarization. If you do the math, so D here has to be 2, right? Because the divisors have degree 2. And if you do the math, you're going to see that the canonical polarization for the union of two lines is the function that takes value 1. It's the constant function 1, right? So that means that in the semi-stability definition, this Q of Y is always 1. But delta is 1 as well, because the two lines intersect in a point. And the degree is an integer number. So that means that for a sheaf, torsion free rank 1 sheaf to be canonically semi-stable of degree 2, it must be invertible, and it must have degree 1, 1. So that means that in our example, right, if I want to study limits of divisors, I can use this moduli of semi-stable sheaves to explain P plus Q, which has degree 1, 1. But it fails to see R plus S. In fact, what it sees is the degeneration of P plus Q, which doesn't explain to you R plus S. So as I said, it's a nice construction. It's the first of its kind. It has applications, but for divisors, it's not so good. So let me go back to the statement. And let me mention that it's not good was already known, actually. Because if you look at the work by Eisenbud and Harris in the 80s, where they defined limit linear series, they observed that in order to capture the limits of divisors, we need to consider sheaves of different multi-degrees. So in the example that we're considering, right, their idea was the following. Instead of looking at the limit of the divisor, what we can do is the following. The divisor is the zero locus of a section of a line bundle, in this case O of 1, and I can consider the limit of the section instead of the divisor. So that means taking the limit of the sheaf and the limit of the section. Right? So the sheaf degenerates to O of 1, of course, but it's not the unique degeneration. In fact, for curves of this kind, we can have all possible multi-degrees. And if we view this limit as a section of a line bundle of degree 2, 0, actually you see that it's a section that vanishes on the whole line M, but doesn't vanish on L. In fact, on L, it has the node and Q as 0. So that's the degree 2, the node and Q. As a section of a line bundle of degree 2, 0. If I look at the limit as a section of a line bundle of degree 0, 2, by analogy, I have a section that vanishes on L and has the node and P as a 0 on L. So looking at the extremes, I get P and Q, and I get P plus Q. So that's one way of seeing things, right? To look at the sheaves in degree 2, 0 and in degree 0, 2. But it's impossible that both of these sheaves are semi-stable. Right? So that construction, maybe it's not a good construction for this kind of problems here. In fact, Osserman, in the beginning of a millennium, maybe, he considers even more sheaves. Right? Instead of considering just extreme multi-degrees, he considers all multi-degrees. And in fact, I mean, I did some work with him, and we observed that they're actually necessary. Just look at the extremes, you don't explain all the limits of divisors. So that's how we stand now. I mean, we have to consider more sheaves, right? Maybe even more sheaves. And that's why that Omid and I took the full step of considering all sheaves that arise in the limit. So considering this Z inside of J bar of X. Okay, so that's what I want to say about motivation, and now I'll try to explain what this Z is. Any questions so far? Okay, so in order to explain what Z is, remember that J bar of X is a stack. And I don't know how to describe things inside a stack. I have to use an atlas. And there is a construction, of course, of J bar X as a quotient, right? But it's not appropriate for us. It's constructed as a substack of the stack of all coherent sheaves. And you can construct that using the notion of regularity and quote schemes. So basically construct your, you view your sheaves as quotients of twists of the trivial sheaf of some rank. It's not appropriate for us. You don't see the torsion freeness that way anyway. So we need a different atlas, and it would be nice if the atlas were global, and that's what we get. So I'm going to explain to you an atlas that we construct, and it's a global atlas, and it's a useful atlas for what we want to do. So what do I mean by an atlas? I will describe J bar X as the quotient of a projective, well, not really projective, well, the quotient of a scheme by a group action. Okay. So, and now I have to talk a bit about combinatorics. So, associated to a nodal curve, I have the dual graph. This is not the dual graph, it's close. I pick V is the set of irreducible components, and E is the set of reducible nodes. That means points of intersection of components. Right? And I consider the graph associated. So an edge connects two vertices if the corresponding node lies on the corresponding two components, is in the intersection of them. So that's the graph that we use. And associated to this graph, I mean, we can put some orientation to the edges. In fact, I denote by this E here, the set of oriented edges. So each edge has two orientations. So we have a 2-to-1 forgetful map. And I can pick an orientation which is just a splitting of this finite map. Okay? So that's the combinatorics. And associated to it, I have a complex of cochains, the cochain complex of the graph. So C0 is the set of functions from V to R. C1 is the set of functions from the oriented edges to R, satisfying this condition here, that the value for a given edge, oriented edge, is minus the value for the edge with the reverse orientation. So the bar stands for the reverse orientation. So we have these functions and we have these two maps. The degree map is just the sum of the values of my function mu. And this D map takes into consideration the structure of the graph. So D of alpha is a function that on V takes the value which is the sum of the alpha e's for all oriented edges that have as target V. So you look at all the edges that contain V, look at those with orientation that points to V, and you sum the alpha e's. So that's the cochain complex, well, without the degree here, of the graph. With the degree, what we have is a right exact sequence of vector spaces. The kernel of D is the loop space. It's H1, the cohomology group, H1 of GR, and it sort of is generated by the loops, the circuits on the graph. And that's how we're going to get the atlas. The atlas is going to be the quotient of a certain scheme omega that I will describe by the action of this product of the loop group. Notice that here I'm taking coefficients in Z. Right? And this torus here, GMV over GM, is a torus of dimension, the number of vertices -1. And in fact, we can view it by using the degree map with integral coefficients, taking the dual map on the characters. So that's this GMV over GM. So we have two groups acting on this omega. Right? I explain the groups, and I'll explain omega. So omega is a vibration over this P of X, which is the product of the compactified Jacobians of the reducible components. So a point on P of X parameterizes a collection of torsion-free rank 1 sheaves, one on each component of XP. Each of an assigned degree BV So B is an element of C naught, right? So the degree of B, which is the sum of the BVs, must be D, because I'm parameterizing sheaves of degree D. And B is chosen. I can just choose to be anything, just fix one. So omega is a fibration over this P of X. And it's a fibration. I mean, all the fibers are the same. And the fibers are these. It's a product of the same schema R over the edges of E. So as many copies of R as I have edges in my graph. Right? And this R is the doubly infinite chain of rational curves. So think of a chain of rational curves, and you don't stop. You keep on going to the right and to the left. All right, so how can this parameterize sheaves? So let me explain briefly how this is done. So how is omega parameter space for torsion-free rank-bound sheaves? So the idea is the following. First of all, I mean, when I give a point of P of X, I'm giving a collection of sheaves, one on each component. So to get a sheaf on the whole X, I just glue them together. Right? So I have to identify the sheaves over the nodes. Over the nodes, I mean, on each component, a node is a simple point. So I'm identifying spaces of dimension 1. To identify spaces of dimension 1, I just need an element of GM, of the multiplicative group of K star. And that's how it's done, actually. So the components of RE are products of P1, right? I'm taking a product of this chain of rational curves that it decomposes then as a union of products of P1s. And they're indexed by C1 of GZ. So what I can do is I can index the irreducible components of every chain by Z, right? And that's one number for each edge, so that's an element of C1 of GZ. Okay. So R of E is a union of infinitely many components, and they're all the same, but they're indexed by this C1 of GZ. And the idea is that we may view the component indexed by 0, right, the zero cochain, as parameterizing gluing data at the nodes of the sheaves that I'm giving on every component. So, in fact, I mean, they're gluing data only if you avoid 0 and infinity, of course, if you are in GN, in the multiplicative group. Right? But you can also do some gluing. It's a degenerate gluing also if you look at 0 and infinity. Then you get the torsion-free sheets. So that's what I do over that component. And what do I do over the other components? Well, the component parameterized by alpha, I see it as parameterizing gluing data not for the sheaves LV, but sheaves obtained by modifying the LV using the nodes. So that's what I do. Oh, just a problem. I'm sorry. Okay. So this is the modification. So you can recall here the cochain complex, right? This alpha E, so the target is V. So that's it. Right? So I'm modifying my sheaves. And since the cochain complex with the augmented map, the degree, is right exact, in fact, I can get any multi-degree that I want by modifying the LVs with this alpha, with some alpha. So that's why I could pick just any multi-degree to start with. The P that appeared before, so I'm not going to go back there. I can just start with anything because I will get all possible multi-degrees by doing this. And by gluing these sheaves for all possible multi-degrees, I get all possible torsion-free rank-bound sheaves. So omega parameterizes all torsion-free rank-bound sheaves. But there is redundancy. You can see the redundancy here if I pick alpha in H1. Because if it's in H1, then you can see that the degree of LV is the same as the degree of LV alpha. Right? So LV alpha is just another sheaf parameterized by the same compactified Jacobian that I had before. Okay, so that means that H1 acts on the base of my fibration, and it actually acts on the fibration itself, on the total space as well. So it's an element of redundancy, and I have to mod it out. This action of H1 may move fibers, actually, but it's a good action. It's free. So it's a free action. So the quotient is good. It's the action of the torus that, even though it fixes the fibers, that's the bad action that leads us to a stack. And what's the action of this torus? So what happens is that if I assign the gluing data at the nodes, different gluing data would give you the same sheaf abstractly. So it's this action of GM mod GM that resolves, the quotient resolves that redundancy. Okay, so that's my omega in a nutshell. I don't have time for much details, but are there any questions? Okay, so now I have a global atlas for my compactified Jacobian. So then I can rephrase my theorem and give more details. Our theorem. And so Z is connected to a substack, and I can describe it by describing the inverse image in omega. So that inverse image is the disjoint union of translates under the loop space and under the loop group of a certain subscheme of a fiber of the fibration. So what I have to describe now is what this subscheme is. So in fact, the Z, I mean, since the action of H1 just translates things, Z is actually a quotient of Y by the torus. So that's the statement that I had before, that Z was the quotient of something by a torus. That's this. So now I have to describe Y. And here comes polytopes and toric varieties. The first thing to observe is that R of E, this union of products of P1s, or product of P1s is a toric variety. So I have a union of toric varieties. That's what I call an arrangement of toric varieties. And this particular arrangement is associated to the Voronoi decomposition of this Euclidean space, C1 of GR, with respect to the lattice, C1 of GZ. It's a very simple decomposition because it's a decomposition in hypercubes, right? Centered in the elements of the lattice of C1 of GZ. Let me give you an example. And that's the case where G has just two edges. Then here you see the points of the lattice, and the Voronoi cells are the square that you see there. So the cells consist of the points that are closer to the center than to any other point of the lattice. So in general, what you get are hypercubes if the points are distributed equally, like that. So that's Voronoi decomposition of R2 for this particular graph. In general, it's a decomposition of hypercubes. Okay? So in order to give a subvariety of R of E or a subscheme of R of E, what I'm going to do is to use polytopes, but polytopes arranged in a different form. They're not going to be simply hypercubes. So there are actually 6 different ways to describe my Y, the subscheme of R of E. And first, and that's what I'm going to present to you, as the toric arrangement of a polytope decomposition, not of C1 of GR, but of H0 of R, which is the kernel of the degree map. present this to you. I said abstractly because you don't see this embedded into RE. Right? It's just an abstract variety. But concretely, we can see this, we can see Y as the toric arrangement of a collection of sub-polytopes of the Voronoi decomposition in hypercubes of C1 of GR. So that way you get the toric varieties, the corresponding toric varieties inside R of V. There is a third description, which is more complete. We describe it locally as union of subvarieties of certain components of RE. So I specify the components, the products of P1s that I want to consider, and in each of these components, I give equations. They're very explicit for the component of Y that lives in that component of R of V. Also, I can describe it locally as a union of orbits under the action. And I can do it globally, given a collection of explicit equations, global equations inside R of E. So instead of looking at each component and give an equation there, I look at the full thing and give an equation, a set of infinite equations for the full thing. And 6, as an explicit equivariant degeneration of the torus, so that the quotient is an explicit degeneration of a point. So there are 6 ways, and we do that to describe this Y, and I'll explain just one of the ways. Okay, so Y is going to be given in terms of the 2 data that I need to describe Y. There is this L, which is a length function on the edges of the graph. So my graph becomes a metric graph. And M is what we call a twist, is an element of C1 of GC. So for each F, for each function on the vertices, integer function, I define this quotient here. So this is simply F evaluated on the difference between the value of F on the target of E and the source of E, divided by L of E and twisted and modified by this M of E. Right? So T of E is the target of E and S of E is the source of E. This is not necessarily an integer, but I define an element of C1 of G of R, but the coefficients, the values are actually in the half integers. And I define this to be the delta, if it's an integer. If not, I take the floor of that rational number and add half. Okay? So it's either an integer or a half integer. And I consider this cube here. So I pick dm of f, and I'm allowed to add x as with absolute value at most half, but x must be 0 at the edges where it's not an integer. Okay? So I'm describing a point which is a sort of cube inside of C1 of GR, but it's not a cube of maximal dimension. It might have smaller dimension, and it's centered in dm of f. Now, there's a natural map from the cochain complex from C1 to H0 of R. It's a surjection. And what I do, and that's another theorem, is I pick the image of each of these each of these cubes. And what I claim is that I get a polytope decomposition of H0 of R, and the associated toric arrangement is isomorphic to Y. So here you go, very explicitly describing the structure of Y as a scheme. Let me just tell you what happens in the example that we had before. So let me go back to the example. All right. So in this situation here, right, we have the surjection. You can look at the surjection as inside C1 as a projection. Right? So we can view this in here, H0 of R, in R2. Right? And then what we're doing is for every function f, we pick a cube inside this Voronoi decomposition. So it might be a full hypercube. Right? So that means that the point is this one. So it could be one of these. Or it could be a point centered in one of the edges of the hypercube, and then the cube is actually, in this case, a segment. So this is one possibility, for instance. And then the projection is just a decomposition of, in this case, a line into segments. Now, this is not the only possibility. You could actually, for instance, start here, and again go to here, and then go one more, and then you add this cube here. So there are several possibilities that that Y can have, and these possibilities are described in terms of L and N. And these are all the possibilities. Okay. So any questions here? Okay. So as I said, this is just one way of describing Y, but it's very explicit, and you can play around and get beautiful pictures, and of course in a higher dimension. Not so high, because then you cannot draw, but. So what I want to do now is to explain what we can do with this. So what now? So I described to you the limit of an invertible sheaf in that stack. So I have this Z, this substack. What can I do with that? So the idea is that we can use this to construct a new compactified Jacobian. So one that maybe could be more useful for divisors, and I'll explain that, as a substack of the Hilbert stack of J bar of X. So what I'm going to do is I'm going to look at Z, which is a closed substack, as a point of the Hilbert stack that parameterizes closed substacks. Now, J bar X is an Artin stack. So you can think that a Hilbert stack of that would be something awful. And I think it is, actually. I think it's not even locally of finite type. So a point might actually lie on infinitely many reducible components of infinite dimension. So that's awful. But I'm not going to consider the whole thing, the whole Hilbert stack, just the substack of that, parameterizing the Z's that I want. And one thing we can do to actually, make things more concrete, and is to replace the whole stack by the stack of effective sheaves. So those are the sheaves that allow for the existence of a section that doesn't vanish on whole components. Right? So the sheaves that have positive degree on every reducible component or on every subcurve. Right? So J bar of X is not of finite type, but the effective sheaves, this is of finite type. And I have reasons to believe, we did some examples, that the substack is actually a scheme. So the new compactified Jacobian will parameterize objects that have to do with stacks, but it's actually a scheme. Okay, so what do I want to do with this new compactified Jacobian? So the idea is to study limit linear series, to define limits of linear series, and to study objects that arise in that way. So here's the idea. That's what we do for smooth curves, right? We pick a line bundle, and then we construct this variety of GRDs, which is fibration by Grassmannians over J bar of X, right? So given a point on J bar of X, parameterizing I, a sheaf I, I'm going to look at subspaces of the space of sections of dimension fixed, R plus 1. I can do the same, right? And in fact, there's work to be done, but if Z is the limit of L eta, and if this invertible sheaf on the general fiber, if I consider a subspace V8 of sections, then I can consider the limit of that pair. it's again going to be a substack, but it might be different from Z. In fact, there is a natural map which collapses some components from W to Z, but in general, the structure of W is similar to the structure of Z. So the description should be very similar. So J bar of X is a stack, GRD of X is a stack, and W and Z are stacks as well. So what I want to think of a limit linear series is this W there. And since these objects are universal, so I can say that a limit linear series is then a family of linear series parameterizing by certain degenerations W of a point. So here's a schematic thing. I'm calling pseudo-linear series because what I put in there, L is a sheaf over X times W, whose fibers over W are torsion-free rank 1 sheaves. Okay, so that means it's not linear, really. It's pseudo-linear in the sense of Hudson, who studied pseudo-divisors in the 80s, I think. Okay. So what's a limit linear series? It's a family of linear series, in a sense, parameterized by this L, which is a family of sheaves, and then this nu, which is just a locally free subsheaf of the push forward. What can we do with this? So let's see how we can construct the divisors out of this. So the idea is that how do we construct divisors? I mean, you take a section of your line bundle and you look at the zero locals of that section. That's what you do for smooth curves. Instead of looking at the section, you can look at the one-dimensional space generated by that section. That's a linear series of rank 0, and we can do the same thing here. Yeah? So instead of sections, what we replace them are rank 0. So the case where nu is invertible. And once you have that, you have the evaluation map. You can take the dual of the evaluation map. And then what you have is a map to an invertible sheaf on the family of curves. Right? And the associated divisor, so the zero locals of that section, is the smallest subscheme F for which this E star factors. You see, it's very similar to what you do for smooth curves. So what you can do for smooth curves. And I must point out that, in fact, that there will be a point T of W such that this F is actually the zero locals of that particular section, of that particular sheaf. So L is a family of sheaves, but there's going to be a sheaf parameterized by a certain point where F is just the zero locals of that section. But this T can have negative dimension. So that's the interesting thing. If you want to look at the divisors, you have to put sheaves that are not simple. So having negative dimension means that LT has a large automorphism group, and that's only possible when you add sheaves that are not simple. So invertible sheaves have dimension 0. So these are special sheaves. And another thing that you can do, you can construct, so that's another thing you do for linear series, you can construct a map to not to projective space, but to something else. How do you do that? Well, given a point, you can evaluate the sections at that point. Now, it's not just into, so that's what you do, right? You restrict it to X. And then you get something which, in case it's a surjection for every point of W, that means that you have a section of the projectivized bundle here, PW of U star. A section means a subscheme, right? So a point on the Hilbert scheme. So the idea is that you want a space that parameterizes all these surjections. And I'm just denoting it by its CP of nu star, and I'm not going to explain what it is. I just point out that in the case where this E of X is surjective, it actually corresponds to a point of a product of projective spaces. So I can pick all the points of dimension 0 of W, right? And so I'm looking at this E of X, which is a continuous thing, but I'm looking just at what happens in dimension 0. because the other points, you're going to have a degeneration of that. Right? So this E of x corresponds to a point on this product satisfying certain conditions. So what conditions are, I'm not going to explain. So I'm sorry, I'm a bit over an hour, I think, but that's it. Thank you for your attention.
Thank you, Eduardo. Are there questions?
I have a question, perhaps.
Go ahead, Marco.
Okay.
So, Eduardo, if I understand things correctly, you take a family of curves with a sheaf on it, and you look at how it can degenerate, right? And this is a family of reduced connected curves, okay? And what about the reverse problem? Say you have a sheaf on a reduced connected curve, say a chain of lines. How can you say whether that sheaf is a limit of, I don't know, line bundles on a complete intersection curve?
Right. So this is the kind of question that you want to pose for I mean, you want to impose some conditions, right? You want that the general curve be a complete intersection, for instance. So it's a special family, maybe. It's not the kind of question that I address. Of course, here you can answer this question, right? So if your sheaf is part of a certain substack Z, it rises as a limit. So you can actually answer that question in this special situation. In a more general situation, I don't know. Even for irreducible curves, for instance, it's known for curves which are not locally planar, the compactification of the Jacobian is not irreducible. So there might be sheaves which are not limits of invertible sheaves. Of course, I mean, you want to consider a family degenerated to the curve, so you could you can allow for more stuff. But yeah, so it's a difficult question actually, and it's a question that I don't address here particularly because, as I pointed out, I mean, you need more sheaves, not just one sheaf to describe limits of divisors. So it's actually a collection of sheaves that I want to pick at the limit curve that I want to ask whether all of them arise as the degeneration of a single invertible sheaf.
So Eduardo.
Okay, Eduardo, thank you.
Okay.
I may bother you again with similar questions later on. Thank you.
Please do.
So Eduardo, very sort of naive question. In that nice example that you gave with the conics, of course that is not a stable curve, but in that example, what limits would you recover in this compactification?
Exactly. So let me go back to it maybe, and to the point where you see, I mean, the idea is that you pick not just one single limit, but a collection of limits. And I'm going back to the example in just a moment. Yeah, here, maybe. Yes, that's the idea here. You see, I mean, you actually pick all of the limits of the line bundle. So you're going to have a limit of degree 2, 0, of degree 1, 1, and degree 0, 2. And the idea is that instead of picking just one sheaf, you pick all of them, and you pick all of the limits. So in this example here, right, I will pick the section that gives rise to P plus Q. It's a section of a line bundle of degree 1, 1, but also the section of a line bundle of degree 2, 0, and a section of a line bundle of degree 0, 2, as I described here. So the idea is that in this particular situation, you can actually point out which section gives you your divisor, which is the section of a degree 1, 1 line bundle. Right? Mm-hmm. But it might be a section of a different line bundle, the line bundle of degree 2, 0, right? Which is the case with R plus S, right? Which is the limit of the intersection with L. So by not fixing the multi-degree, I'm allowing for all of these cases. Mm-hmm. So that's what I'm going to pick. I'm going to pick all of these sections.
Mm-hmm. Thank you. Are there more questions?
Eduardo?
Yes.
At the beginning of your talk, you mentioned that the classical work had important applications. And what kind of application you hope to get from this new setup, which were not accessible for by the previous methods?
Right. So, so what I have in mind, so we're going back to here, right? So one thing to observe here is that these new compactifications, of course, we plan to get a relative compactification also over the moduli stable curves. That's where the interesting applications would be. And this new compactification would be a fine compactification. So it's going to be a universal thing. So I didn't emphasize this here, but I mean, all of these stacks that I'm considering, there is a universal family or a family that they parameterize. So there are constructions that you can do only if you have a family. So that's what we're hoping for. So to use the universality, the universal sheaf, and to construct, to get a finer object that we can tell more about. So for instance, to consider the tangent space at a point, it's very simple if you have a universal object. Just look at deformations, infinitesimal deformations of that universal object. So I don't have any specific application in mind. I just considered the problem, and everything basically arose from that work with Brian Osserman when I realized that more sheaves give more information, and I was chasing that information. But if there's maybe applications that were not possible before, maybe it's because now we have universal sheaves.
Okay, thank you.
Are there more questions? So if not, let's thank Eduardo again.
Thank you.
And we meet again next Wednesday.
Okay, thank you all.
Obrigada, Eduardo.
Obrigado, Eduardo.
Um grande abraço para todo mundo aí.
Tchau.